In this lecture, we're going to look at Bernoulli Theorem, and the starting point for the Bernoulli Theorem is the Euler equation. So the Euler equation we've already seen is that the acceleration of the fluid is equal to the forces because of the gradient of pressure and body forces. So in this case, we consider gravity to be the only body force, but if required, it can be represented in terms of any other force as well. But for now, let us continue with gravity being the only body force. We have obviously dropped viscosity, meaning that the flow is inviscid. And in deriving all this, we have also assumed incompressibility. So the flow is incompressible. So let us write down the expression. So we have rho del ui del t plus uj del ui del xj is equal to minus, or in fact, let us do everything in vector form. Let us not go to index notation. So we have rho del u del t plus u dot nabla operating on u is equal to minus gradient of pressure. So now the body force we can also represent. So now this rho g, so this should be plus rho g vector. In the z momentum equation, the rho g vector would come out to be minus rho g. Otherwise, it's 0. For the x momentum equation, there is no gravity component, and so all those terms are 0. So we can represent rho g vector as minus of the gradient of a potential. So minus rho g z. So this is equal to minus rho g ez. Basically, it is the same thing as rho g vector. So we can write it in terms of this. It's nothing but the force being proportional to minus of the gradient of a potential. Alright. So moving on, we can make use of the vector identity that u dot nabla u is equal to half mod u square minus u cross nabla cross u. Let us prove this little identity with the knowledge of index notations. Let us start with this u cross nabla cross u. So the ith component of this will be equal to epsilon ijk uj and the kth component of this. Basically, I have taken the first cross product. This as the first term, this as the other term. Now we can expand this second term further, and we can write it as epsilon ijk uj. Now the second term is, so the kth component of this, epsilon k lm del x l um. So now this becomes epsilon ijk epsilon k lm uj del x l um. Now we can make use of the epsilon delta relationship, which says, So let us write it down in terms of this. So let us cycle the index over here. So this becomes epsilon kij, epsilon klm. So we can cycle it without losing any property of the alternating tensor. So this is equal to delta IL delta Jm minus delta Im delta JL. This is called as the epsilon delta relationship. So you substituting this in this equation, we have u cross nabla cross u, its ith component. This is equal to, now substituting this, delta IL delta Jm minus delta Im delta JL times uj del del xl um. So this is delta IL delta Jm uj del del xl minus delta Im delta JL uj del del xl. So now these two terms will be non-zero only when I equal to L and J equal to M. So let us make that index substitution over here. So this becomes uj del uj del xi minus, now this combination of terms will be non-zero when I equal to M and J equal to L. So when I equal to M, this term becomes UL del del XL of UI, and this is nothing but del del XI of UJ square, but there will be a half. This first term is this, while the second term is UL del UI del XL. So now what we have found so far is U cross nabla cross U. This, the ith component of this particular vector, is equal to half del del xi of uj, that is uj square, minus ul del ui del xl. Now let us convert it back to pure vector notation. So this is nothing but half gradient of the magnitude of u square, and this thing is u dot nabla operating on u. So from this we can write u dot nabla operating on u is equal to half gradient of mod u square minus u cross omega, because omega is the vorticity and it is defined as the curl of the velocity. So we have proved this particular identity. Now we can move forward. So what do we have? We have rho del u del t plus rho half gradient of mod u square minus u cross omega is equal to minus gradient of pressure minus gradient of rho gz. Okay, so let us write it in this form. So this is half rho gradient of mod u square plus gradient of pressure plus gradient of rho gz is equal to rho u cross omega. Now let us try to integrate this entire equation from point 1 to point 2. So let the vector be dl. Okay, so when we take a dot product, so let's just take a dot product for now. So we have this. So let us look deeply into what the dot product means. So let us look at this. So gradient of P dot dl. Right? So these dl's are vectors. Okay. Uh, So this is essentially del P del x I plus del P del y j plus del P del z k. This is the gradient of the pressure. And when you take a dot product with dxi plus dyj plus dzk, we see that this is tantamount to del P del x dx plus del P del y dy plus del P del z dz, and this is nothing but dp. So the gradient of any scalar dotted with the dl vector is nothing but dp. That is the, if you integrate this, is nothing but finding out the difference between the values of this variable between 2 points. Because when you integrate this over say point 1 to 2, it's simply dp point 1 to 2, and it is nothing but p2 minus p1. Okay, so the gradient appears over here, here and here. So thus when we take a dl, when we take a dl of those terms, we would simply have the d of those terms. So the first term remains as it is. The second term becomes half rho d of mod u square. The third term becomes d of p. The fourth term becomes d of rho gz. And lastly, the term on the right hand side is u cross omega cross dl vector. So we can write this as rho du vector del u vector del t dot dl plus d of rho by 2 mod u square, where we have assumed that rho is constant. If rho is not constant, we cannot incorporate this into this particular equation, plus d, so plus p plus rho gz equal to rho u cross omega dot dl. Now let us say that the flow is steady. So far what have we assumed? So if we assume that the flow is steady, we have already assumed it is inviscid, incompressible. So if it is steady, inviscid, incompressible, we simply have this. We simply have this. Now in this, if we choose the direction of dl, so if we integrate this from point 1 to 2, and if dl is chosen along a streamline, so if dl is chosen along a streamline, it means that the dl and the velocity vector are collinear. So if dl and u are collinear, u cross omega dot dl will become 0, because the interpretation of a cross b dot c, so if a and b are this and if c is this, so it is like the volume of the cube formed by a, b and c. So that is the physical meaning. So if two of these vectors are collinear, then this will vanish. So if dl is chosen along a streamline, then this term becomes 0, and we are simply left with d of rho upon 2 mod u square plus p plus rho gz equal to 0, and that eventually implies that rho by 2 mod u square plus p plus rho gz is equal to constant. So if we choose dl along a streamline, so apart from this, integration along streamline, then we have the Bernoulli equation appearing. This particular set of terms is called as the Bernoulli function. So when we integrate it from 1 to 2, if we integrate this from 1 to 2, we have rho upon 2 mod u square at 1 plus p1 plus rho gz1 is equal to rho upon 2 mod u2 square plus p2 plus rho gz2. Remember that in order to obtain this with a general form of vorticity, we have not yet looked at a specific constraint on the vorticity, but if we integrate it along a streamline, we obtain the Bernoulli equation. Now, the second thing that can happen, so this is case A. The second case that can happen is the flow is irrotational. So if the flow is irrotational, meaning omega is 0, right? If omega is 0, then the term appearing on the right hand side identically becomes 0 regardless of the choice of integration. This entire term will be 0 because omega will be equal to 0. So then, regardless of integration path, so if it becomes 0, then again we obtain this same relationship and we are able to get back the Bernoulli equation. So in a domain, if we know that the velocity field is irrotational, we can simply apply Bernoulli's theorem between any 2 points. We can integrate it between any arbitrary points. However, if the flow is not given to be irrotational, we can apply Bernoulli's theorem between 2 points lying on the same streamline. The third constraint, or rather the third case, is some combination of u omega dot dl so that it is 0 during integration. So some certain choice of this, although this is very abstract in nature, there can be some mathematical situations where this can be true, and in that case also the Bernoulli equation can be applied between any 2 points on the streamline. Now what about the unsteady term? We can sort of keep the unsteady term, we don't need to drop it in any kind of approximation, but there is a certain class of flow in which it has a very special form. Let us consider that the flow is irrotational. If the flow is irrotational, then the vorticity becomes equal to 0. So if the flow does not have any vorticity, then the curl of the velocity is equal to 0, meaning that the velocity can be represented as the gradient of a potential. This particular potential is called as the velocity potential. So the curl of the velocity being 0, so if curl of a vector is 0, then the vector can be represented as the gradient of a scalar. And this is nothing but that statement. So in that case, the first term becomes rho del grad phi del t dot dl. The second term is d of rho by 2 mod u square plus p plus rho g z is equal to rho u cross omega dot dl. So now this particular term is simply rho del t of this. This is nothing but d phi. So this becomes rho del t of d phi. And already we have a d term over here. So we can combine this. So essentially it becomes d of rho del phi by del t plus rho upon 2 mod gradient of phi square plus p plus rho g z is equal to rho u cross omega dot dl. So but we have already assumed that the flow is irrotational, so this particular term vanish, and so we have the modified Bernoulli theorem for unsteady flows. But this is only valid for the case of irrotational flows where the right hand side vanishes. In case it is not irrotational, the right hand side has to be written, and moreover we cannot represent the velocity in the form of the gradient of a potential. Now you may think that all this is valid for inviscid flows, but there is a certain special case where the viscosity is present, but still we can arrive at the Bernoulli equation. Let us write down the Navier-Stokes equation for a Newtonian fluid. Now this particular term, which is mu, this actually, I mean, if we drop the viscosity for now, we want to represent the Laplacian of u in terms of something else, meaning that we can represent it in terms of two gradient operators and one velocity vector. So let us look at this particular term, nabla cross u. Okay, so nabla cross u is epsilon ijk del x j. So if I write down the ith component of this, nabla cross u, its kth component, and this is epsilon ijk del x j epsilon klm del x l u m, and this is epsilon ijk epsilon klm del x j del x l u m. Now we can make use of the epsilon delta relationship and write this as delta il delta jm minus delta im delta lj times del xj del xl um, and this is nothing but, so I will be equal to l and j will be equal to m. So del x, so l is I, so del xi del um del xm. The second term is I is equal to m and l is equal to j. So del xl del xl ui, and this is the divergence of the velocity. So this is del xi, divergence of the velocity, minus, now this is the Laplacian of the velocity. So essentially it is simply this, assuming an incompressible flow. So therefore nabla cross u is equal to minus Laplacian of u, and this is nothing but nabla cross omega. So in the Navier-Stokes equation, when we substitute this particular identity, assuming this of course, we end up with this particular term. And if we go back to the assumption behind the unsteady Bernoulli equation, if the flow is irrotational, then this particular term also vanishes for irrotational flow. And if this particular term vanishes, we get back the Euler equations and we know the rest of the steps to go from the Euler equation to the unsteady Bernoulli equation. So even though viscosity is there, we are able to relax the condition for viscosity in the case of irrotational flows, because irrotational flows cause the manifestation of viscosity to become zero. It may strike quite odd that we've already discussed many times throughout the lecture so far that the stress should not depend on rotationality, and thus the vorticity should not have any relationship with the viscous stress. But the fact is, it is not just vorticity which has a relationship with the viscous stress, it is the curl of the vorticity, meaning it is capturing how vorticity is changing in the domain. If vorticity is changing in the domain, that is because of the presence of viscosity. Vorticity, if if a flow is irrotational at a certain point of time, in the absence of vorticity, in the absence of viscosity, the vorticity will not change. So if we consider a plate like this and a fluid element like this, it is because of the effect of viscosity that the velocity over here is zero at the plate, no slip, while the velocity over here is something like this. So the velocity field varies something like this. And so these elements are, it's trying to rotate. It's like when you jump off a moving car, I don't recommend you doing that. So your feet are grounded, but your body still wants to go like this. So you sort of tumble. So it is viscosity which is causing this no slip velocity profile, and it is imparting rotationality. So viscosity is a major mechanism of imparting rotationality, and that is why the the rotationality also appears in the Navier-Stokes equation as this. But when we assume that the flow is irrotational, this particular term will vanish.